Dear ladies and gentlemen, I would like to welcome you to the training workshop on biogas from organic waste, and this is the part on dry digestion. My name is Jan Lieberthal, and I hope you enjoy the following slides. Content of this presentation is, first of all, definition and basics on dry digestion. Then I would like to discuss continuous operations, in particular plug flow reactors. And I would like to go on then with discontinuous operations. And here major focus will be on the very specific garage style digesters. At the end, of course, I would like to sum up and come to some conclusions. Dry digestion, what is the definition of dry digestions? Of course, the water content in general has a major impact on the degradation process on the one side. So any biological process needs water, and that's why the water content, the water availability is a crucial factor for biological processes, and anaerobic digestion is no exemption here. And of course, the material handling. If you imagine you want to pump a substrate, then the dry matter content has a large impact on the viscosity, on the capability to flow. So that's why material handling is also quite dependent on the water content. These two factors have therefore a large impact on technical anaerobic digestion process. And there is a certain range in which anaerobic digestion processes are operated. And usually the term dry digestion or dry fermentation refers to the processing of the substrate with a high total solid content. And for the technical application, the substrate content is only one aspect here. Much more important is, of course, the dry matter content in the digester. So the term dry digestion or dry fermentation refers to substrate with a high total solid content, but more important and the actual critical term is the dry matter content inside the digester. And I have here two digesters, graphs of two digesters, and as you can see, the necessary volume for the same retention time is doubled when you reduce the dry matter content from 20 to 10%. Because from 20 to 10% the water content doubles, and for the same retention time in the system you would require twice as much digester volume. That's why one of the major advantages of processing high solid substrates with a high total solid content inside the digester is that you need less digester volume. The digester volume with the same retention time can be reduced the higher the total solid content inside the digester is. Consequently, you also have less material to deal with, so simply the mass of water and the overall mass of the substrate is reduced. You have less separation problems in the digester, which means you have no sedimentation of heavy materials, stones, metals, things like that you might have in organic waste fractions. So you don't have sedimentation of such fractions that much. And you also have no floating of plastics and swimmable materials. This is also an advantage. This is less water required for the conditioning of the material, so you have less recycling water streams, you have less water to deal in the end of the process with. So you don't have to have a cleaning up of process water, which is quite a cost factor for some of the wet fermentation systems. And due to the systems you have for substrate and digester medium transportation handling, the process is rather robust towards disturbing materials. If you have sand or stones, things like that in the system, it's easier to handle with pumps and transportation systems which have to handle solid materials. Challenges of this process are mixing issues, because you have a high viscosity, so the material flows and mixes very slowly. You need a lot of force to mix this. Material handling, you cannot pump such thick viscous substrates with standard conventional water pumps. So you need to make sure that your transportation systems can handle the substrates. And you usually have also reduced yields, gas yields, and degradation rates due to the high total solid content. And this is also a minor disadvantage. Coming to the next slide, we have an overview over the two major technologies in dry digestion. The one thing is the so-called batch mode systems. Batch mode means you feed the substrate into a reactor and let it sit for the digestion time. The opposite of this is the continuous mode. In the continuous mode, you have a constant feed into the system and a constant output out of the system. In the batch mode, practical relevance, so plants we have seen in a certain number in technical applications, are systems with percolation. This is the so-called garage style digester. So you feed the substrate into a garage and percolate a liquid over it. The liquid trickles through the substrate and is recycled, recircled again and again in order to enhance the anaerobic degradation process. You can add inoculum to the substrate, or you simply can try to wash out the substrates via the percolation process. These are the two major steps here. The one would be the first in the list here. This is the one-phase system where you add inoculum. The second is the two-phase, where you would like to separate the methanogenic phase. Separate means you transport the washed out acids into a secondary methanization reactor. So you have a hydrolysis and acidification in the garage and a methanogenesis in a secondary digester. But I must say that in practice it has been very difficult to really stop methane production in the garage. So more or less these two systems are somewhat overlapping, so you have also methane production in a rather two-phase system. So what I want to say is that you can speed up the process by high percolation rate, you can speed up acidification, but at the end you also will have in this digester methane production. This is almost not to be avoided. Continuous mode, we have several relevant systems. Two-phase process with continuous washout of the substrate in a plug flow system has been developed, and I think there was a pilot plant, but it never came to a lot of installations in full scale. But the one-phase process plug flow reactor for organic waste, this is a very common system, and I will introduce that to you in following slides. We have most common substrates. As I already said, total solid content is a very important point here. So mainly substrates with a high total solid content are used in anaerobic digestion, dry fermentation systems. Very common it is for separately collected organic fraction of municipal solid waste. So in many countries we have a bin in the households where organic waste is separately collected, and then this material has a high total solid content and can easily be digested in a dry fermentation system. There is also an application, in particular in Germany, for a fraction of municipal solid waste. So there is a treatment of municipal solid waste. It's shredded and then it's sieved, and a certain particle size contains a lot of the organic material, and this is being stabilized prior to landfilling, prior to deposition in a landfill, in order to avoid biological activity on the landfill. And this organic material you also can digest, and dry fermentation systems are reliable technology for this biological stabilization. Last but not least, we also have in the aquaculture sector substrates with a high total solid content. You might think of straw or also energy crops, and mainly the plug flow system has been often used also in the aquaculture context. To continue with the basics of dry fermentation, as I already said, microorganisms require water to take up nutrients, to transport nutrients, and also essential substances. And that's why you can also in experiments, as you can see here in this graph, quite clearly show that the higher the organic material content in the substrate, or the higher the total solid content in the substrate, the lower the gas yield of this substrate is. Limitation of the total solid content is usually said to be around 40% total solids, but I would like to highlight here that this is not only the total solid content, which is then available in higher concentrations. There are also other substances which are in the substrate in elevated concentrations once you reduce the water content. Last but not least, total solid concentration in the substrate and total solid concentration in the digester are two things. First of all, you have a degradation process which reduces total solid content. So you have a fraction of the organic material which goes into the gas phase via the biogas. So you lose total solid, which increases the water content. Second, many processes recirculate liquids, recirculate digestate or separated digestate. So you add water at the front end of the digester in order to achieve a certain total solid concentration in the digester. And this also reduces, of course, the total solid content in the digester. So it's not that obvious to deduce from the total solid concentration of the substrate to the actually total solid concentration, to the actual total solid concentration in the digester. On the next slide, I would like to show you also this fact, what I just mentioned, that also other substances concentrate if you have a low water content. If you have a low water content, yes. One of these is the ammonia concentration. Ammonia is actually a degradation product of any organic nitrogen in the substrate. So any plant material, but also manures, contains organic nitrogen. And once this is degraded, it turns into ammonia. Ammonia concentration can inhibit the process depending on, simply on the concentration. And if you would assume that ammonia concentration around, let's say, 3000 milligrams per liter starts to inhibit the process, then you can see in this little table here that with an increasing total solid concentration, the nitrogen concentration in the substrate, and then consequently also in the digestate, will increase. And the ammonia is not being replaced or going into the gas phase, so it stays mainly in the liquid. So the concentration apparent in the solid material will also be apparent in the liquid phase, assuming that most of the ammonia is degraded. I have stated here a degradation range between 45 and 80%. This depends a little bit on the process, but accordingly you can calculate how high your ammonia concentration will be, and you will soon run into inhibitory conditions with the degradation. If you use substrates like these ones here. And this is a cattle manure here. This is not even a very ammonia-rich substrate, as for instance chicken manure would be. And you can clearly see that you have to keep an eye on the ammonia. Another point here is salt content. In some substrates we have concentrations of salt, and there you also have to check what impact dry digestion would have on this concentration and if this would result in inhibitory conditions. Plug flow digesters, I have already discussed some of the basics on the slides before. Plug flow, the term plug flow is a little bit misleading because it would mean that you have no mixing on the horizontal axis, as you can see it here. Then it would be a perfect plug flow, but this is impossible in the systems you will find in full-scale applications here. So there will be a horizontal mixing. It is even wanted that you have such a horizontal mixing because this transports your microorganisms. This also makes sure that if you have a little concentration of substrates or a little overloads zone, that you can even balance this out, you can even this out in order to get a continuous and stable anaerobic digestion process. So plug flow would be the ideal system in a chemical reactor. In the full-scale applications of bio-waste, you hardly find a system which is 100% plug flow. The advantages are that, as already said, you have a constant substrate and product flow, and you also have a constant degradation rate. Disadvantage, it's quite a technical effort. You can see here on the right side a picture. These are the substrate lines, and you also can see the pump system up front. So you need to have quite sophisticated pumps to transport this material. And these are usually piston pumps, which require a lot of energy, but they can handle also materials like concrete. So they are built to also resist stones and other disturbing materials. So this is a very reliable system. You might also have issues with mixing the digester. There are several systems, therefore, if we look at the next slide, you can see that there are systems with the mixing on the lateral axis, and also a mixing system where the axis goes straight to the long side of the digester. And you can imagine that to keep such a mixing system really stable and have not a lot of movement of the system during mixing is quite a challenge for the process engineers. However, both have advantages and disadvantages. They are both in full scale available and tested, so I couldn't say that the orientation of the mixing system is a huge issue on these systems. It's just that there are two different systems available. The material of the digester is also available in different systems. You can have them in steel or in concrete. The pictures you can see here, they are in concrete. And usually these systems are operated in a very narrow total solid window. This is in order to avoid sedimentation processes. That's why the total solid concentration is kept quite high. And it shouldn't be too high, because then you get issues with the mixing, with the substrate transportation, and also with the release of the gas out of the digester medium. And the standard post-treatment system of such digester systems is a dewatering step, and then the drier fraction of this dewatering process is usually composted, and the liquid fraction is either used for recycling in the process, or it is spread on arable land, or you need to have treatment in an aerobic wastewater treatment process. When you look at the continuous plug flow reactor in regards of the relation of total solid content, hydraulic retention time, and organic loading rate, you can see that, of course, the higher the total solid content and the lower the hydraulic retention time, the higher the organic loading rate. Make sure that once you calculate that you consider your digestate recycling, or your recycling of the liquid fraction of the digestate after the dewatering process. And other than standard chemical processes where you can put together the basic materials and then they react simply in such a plug flow reactor, the issue of a biological process is, or in particular of the anaerobic digestion process, is that you need to have a mixture of methanogens in your initial feed-in order to avoid acidification. If you have not enough methanogenic microorganisms in your substrate and you have a plug flow, then your digester would simply acidify, and this would lead to a collapse of the process. That's why you need at the very beginning a lot of methanogens, and this you can achieve by either having a horizontal mixing in the digester, or you add inoculum at the very beginning of the process by recirculating digestate. If you have a recirculation process, you also need to pay attention to the fact that in the liquid fraction, then you accumulate dissolvable materials. This can be salts, this can be ammonia. You have to pay attention to that because it adds to the problem of inhibition, and that's why you have to check on this occasionally, and or at the very beginning, maybe in the planning phase, you have to do some calculations how these concentrations actually increase. Here we have continuous plug flow system, an application which is actually operated, or which is offered on the market by the company Dranco OWS Systems. This is the only company who is offering such a system here, because it's a vertical plug flow. The substrate is mixed with digestate and then pumped to the top of the digester, and is then sinking simply forced by gravity to the bottom of the digester, and it's taken out at the bottom. Then a fraction of it is removed out of the process, and the other fraction goes back to be mixed with fresh substrate and fed back to the top of the digester. There's no internal mixing in this process. There's a high throughput, simply due to the fact that you have to add digestate and fresh substrate. And the substrate transportation, the only substrate transportation, is done by a piston pump. And these pumps, as I already said, they are usually used for concrete pumping, so they are quite insensitive to disturbing materials. As already said, this vertical system is only provided by one company. There are quite a lot of applications worldwide, and this is, at least for my understanding, quite an interesting application here. Coming a little bit on the details for solid transportation systems. Usually, as you can see here, this is done by screws, if not by a piston pump. So if you have really solid material, then also a piston pump wouldn't work. And then the standard transportation system is a screw. Usually you have a hopper, as you can see in the right pictures, and sometimes you also have some screws in the hopper, or some turning devices in order to transport solid material to the screw, and then the screw is moving the substrate on a vertical axis usually, or also on horizontal axis, as you can see in the middle picture. Here you have some links for companies who build such plants. There are also some information videos here which are quite interesting, so if you're interested, then check on these websites. The continuous plug flow reactor, to sum up a little bit and to give some general considerations here, we have substrate pumps to handle the material. This is quite a challenge. We have a high energy demand for pumping and mixing due to the high viscosity of the substrate. However, high total solid concentrations allows a high loading rate and then also a very high specific methane production rate from the digester. You need to check on inhibition, which substrates are in your substrate which might be inhibitory. And the post-composting will often require solid-liquid separation, so make sure that you have a plan for your digestate if you consider to build such a plant. Here are some examples of plants. You also find the reference at the bottom, so this is to be downloaded, these brochure where also these plants are described, and I don't want to read these details here now to you. I think this is easy to follow up here. Second technology I wanted to introduce to you is the batch digestion system. As already said, the batch digester is fed to a reactor and then left for the digestion time, and this has the consequence that you have a discontinuous feeding, you have a discontinuous gas production, and you have a discontinuous output out of the system. So you need to make sure that this is considered for your overall plant operation. So the substrate goes into the digester. It can be mixed with digestate, it doesn't have to be. However, it's fed to the digester, then the digester is sealed, then your percolation process starts, and in the first phase you have gas produced, which is mainly CO2, and this gas cannot be used. And of course you have a lot of air in the digester in the first place, so you have a gas where you have to consider what to do with this. Sometimes this gas is also directed to the CHP, but rather as air supply than a combustion gas supply. But anyhow, you need to consider what to do, how to treat this gas with low methane concentrations. Then sooner or later the methane concentration in the gas rises, and then you can start to use the gas as a combustion gas in the CHP unit, for instance, or to upgrade it. Then you need to run a certain percolation regime in order to make sure that your digestate heap is heated up. It's also well percolated to transport substrate and methanogenic microorganisms through the substrate. At a certain point, the uptake of liquid of the digestate will end because the water holding capacity is exceeded, and then your percolation will simply trickle through the digester. Before you open up the digester, I would recommend to stop percolation defined period of time prior to the opening to allow a certain dewatering of the heap, and then you can open the digester at the very end. Make sure that you flush the methane from the digester, and then you can remove the digestate and bring it to the post-treatment process. Advantages of this system: it's a very simple system. You need a wheel loader and several garages in order to treat the substrate. Consequently, the technical requirements are quite low. This also means you have lower investment costs. You have a defined and guaranteed retention time, so there's no mixing of the substrate and maybe short circulation out of the digester, so you have every particle is a certain period of time in the digester. Since you transport your substrate only with a wheel loader, there is no problem with any disturbing materials, stones, metals, whatever, no problem. And you also can separate substrate batches. So once you have maybe inhibitory substances in one batch, or you have some toxic substances in a batch, the problem will usually only occur in this very specific batch. The other garages won't be affected by such a problem. Disadvantages: you have no continuous flow of the input material in biogas, so you have to store substrate, you have to wait until you can feed it in, so there's no continuous processing. You don't have a perfect contact of microorganisms and substrate as in a fully mixed system. You have reduced mixing, and you have also only limited opportunities to control the process. So you cannot increase or reduce feeding rate, you cannot turn up the mixing, things like that. You cannot add some additives which are mixed in the process, things like that. You cannot do in this system. You have a higher area required because the height of the digester is limited due to the compaction of the material at the very bottom of the substrate heap. So the higher your heap of substrate is, the more compaction you have at the bottom, and this would result in a loss of percolation. So at the very end, your substrate wouldn't be able to let percolate through, and that's why the height of the digester is limited, and you need more area for such digestion systems. In general, the substrate need to have a certain porosity during the whole process. So you need also this porosity maintained during the degradation process in order to avoid compaction and enable the percolation process. You need an inoculum to start up the process, which might be not as easy if you don't have a dry digestion process nearby to get some inoculum. And it's a more or less experience-based operation. So if you come with new substrates, you really have to play around to get this going, to make sure that your percolation is stable, to see how your percolation rate and the dewatering is happening. This is not only an easy process, and also the plant commissioning takes some time until you really have the right mixture of inoculum and substrate, and maybe also some structural material which you have to add, percolation strategy, things like that. So this is not a standard process. To come to the gas production, as I already said, it's a discontinuous process. So you have a rising gas production until the peak is achieved, and then methane production will decrease again. And in order to have a constant gas supply to your digester, you need to have several, not to your digester, to your CHP, you need to have several digesters which are operated in a certain time shift. So you feed the one digester, and the next one you feed a week later, the third one a week later, and by doing so you have always one digester in the peak gas production and the other ones around, and by doing so you can achieve a rather constant gas production, as you can see in the lower picture here. As already said, the handling, opening up, closing of the digester leads always to gases of lower quality and might also lead to emissions from the process. To sum up with the selected technical details here on the batch reactor, any substrate has a certain water holding capacity, and the percolation leads to a certain uptake of water until this water holding capacity is reached, and then the water is not stored inside the digester, it's percolating through. So make sure you have an idea how much water your substrate will take up before it starts to give away the water again. Structure and material is needed in order to have an effective percolation. So only if you have certain porosity, a stable porosity, then the liquids get through. And make sure that compaction by the weight of the substrate itself is not too high, and you make sure that the liquids are getting through. Technology options you have from certain providers, they vary usually in the size of the percolation tank. So either percolation strategy is to remove acids as fast as possible, or second strategy is to enable methane production as quick as possible in the digester. Some technologies also include aeration and composting in the garage. Again, make sure that your substrate characteristics and your structure actually allow such a processing. Percolation can transport small particles or salts, and you have to have an eye on precipitation of these in the pipes. This might lead to clogging the pipes. Use of inoculum, this is a question of the operators. Some use this inoculum and some not. So yeah, you have to see what your provider is recommending here and then follow the instructions. Batch retention time is usually 20 to 30 days, and theoretically separate substrate lines are even possible, and the advantage I already mentioned is that process problems resulting from substrate changes are limited to one batch. There are many providers and process variants with different percolation strategies. There's only within the treatment of separately collected of municipal solid waste. This technology is only applied within the treatment of separately collected municipal solid waste. And in the agriculture sector, this technology is not very common, simply due to the fact that you can treat these agricultural substrates much easier in other systems. Post-treatment of the digestate is usually post-composting. There's not always a dewatering step necessary, but you might think of adding some structural material after the composting, after the anaerobic digestion process. Here you can find some, again, some links to some applications. And Beacon is one company, Compotec, Herhoff, as you can find here, are all providers of these systems. Patinger, yeah. So if you are interested, feel free to check out these links here. Post-treatment, as already said, dry digestion is closely linked to the post-treatment. Usually in Europe, the standard treatment of organic material in the past was composting, and consequently most of the systems today are a combination of anaerobic digestion and composting processes. And that's why the main post-treatment process for anaerobic digestion is also composting. And composting can be used for hygienization, because you reach temperatures above 50 degrees in a compost heap if it is well operated. And then you have the necessary hygienization of your substrate, of your digestate. You have also a certain water reduction due to the convection of air through the compost heap. Due to the temperature, water is actually forced out of the compost heap. But you all, of course, need to have structure, and you have to make sure that oxygen is getting into the compost heap, and this is an important way. Otherwise, this is an important factor here. Otherwise, you will simply continue to have methane production in the composting heap, and that would lead to very high emissions, which has been already been proved by some research activities. Afterwards, composted materials is usually sieved, and then you have a high quality compost. Anyhow, you have to make sure that you have a market for this end product. And this is a task for a planning phase, to make sure that at the very end you have processing or a marketing of your end product. Otherwise, you have a lot of issues to remove this end product from your site. Here are some impressions from full-scale plants. Reloader feeding the crushing and the feed-in unit on the right side, on the left side, and on the right side is a little bit different angle of the same hall here. You can see actually a conveyor belt transporting the crushed material into the next processing step. These are mobile sieving units, drum sieve in this case here, and here the composted material is actually conditioned. You can also remove unwanted materials, as you can see here in the foreground of the left-hand picture, that the sieve output, the larger fraction here, contains much more plastics than the fine fraction of the sieving process. However, the quality of your input material into your digestion process rules the quality of the output material. So the cleaner your input material is, the cleaner your output is. So the major target should be to really reduce disturbing materials in the input material. Again, we have some impressions of some full-scale plants here. You also can find in this brochure from the German Biogas Association. I don't want to read all these details here. Please check out in the brochure or here on the slides the major conditions. Here are a couple of pictures of a plant my company has actually built and commissioned, and you can see here also the tunnel for the composting process after the digestion process. Here again, some numbers from plug flow anaerobic digestion plant in Schwarzwald, which has been also built and commissioned by my company. And this is also a plug flow digester, which I already have introduced to do. Finally, to the conclusions of the dry fermentation process. It's an appropriate technology for high solid containing waste materials. It reduces mass, but you have to consider that reduction in water content leads to higher concentrations in total solids, in potentially inhibitory substances. Disturbing and unwanted materials can be handled by most technologies. That's why this technology is favored for substrates out of the municipal solid waste sector. So it can be separately collected organic waste, but also can be pre-treated municipal solid waste. There are two major technology lines. This is the continuous and the discontinuous operated processes. The quality of the input material rules the quality of the output material. This is something to be considered in the planning phase, and of course it's very important for the market, for your end product, and also the quality of your compost at the end. So make sure that you consider during the feasibility and the planning phase what quality your input material has, what gas yield you can expect, and then what market there is for this material. That's it. You can find also my contact data here on the right side of this last slide. And if there are questions, feel free to contact me.